This is a reply to Vincent Wong. What I have here is an interactive Minkowski diagram, similar to the one in the video we were discussing. This shows different paths through space-time and allows you to adjust the reference frame of the diagram by changing the value of u over here. A value of negative 0.5 means this is what events would look like from a reference frame that is moving at 50% of the speed of light to the left. A value of 0.8 would show you what the events look like from a reference frame that is moving at 80% of the speed of light to the right. What I have drawn here is how seconds would tick by for Alice and Bob. This line shows Alice's journey through space-time. And these lines over here are Bob's journey through space-time. Alice is standing still in her own reference frame, and each dot represents one more second in her reference frame. Bob moves at 80% of the speed of light to the right. If we shift our reference frame over, we can see that he does so for 1, 2, 3 seconds. After 3 seconds, he changes velocity again, so he's moving at 80% of the speed of light to the left relative to Alice. So let's see what that looks like. Shift it over here. And he goes on at that speed for another 3 seconds. Overall, a total of 6 seconds has passed for Bob, while 10 seconds have passed for Alice. If faster-than-light communication were possible, Alice could send a message from this event over here to this event over here, since this event is 1/3 of a second further in the future than this event. See, this happens at 3 seconds, this happens at 3.333 seconds, so 1/3 of a second later. If faster-than-light communication were possible, this communication should have been possible. However, in Bob's reference frame, this looks a little different. In Bob's reference frame, this message has traveled to him from the future, from 3 seconds in the future, from 5 seconds to 2 seconds, from timestamp 5 seconds to timestamp 2 seconds. This would be effectively time travel. If he then decided to retransmit this information at second 3 and send it over here to Alice at second 3 1/3, that should also be possible with faster-than-light communication. The problem is that in Alice's reference frame, this all happens at second 2. She receives the message at second 2, but she transmitted the message at second 3. So this would create an issue where she receives her own message before she sends it. This is why, if it were possible to send matter or information faster than light, we would be able to send matter or information back in time. If you want to play with these things yourself, you can use this interactive Minkowski diagram. I've included a link to it below. You can click and drag the events around to see how they change and how they look different from different reference frames. For example, if you have an event here, an event pretty far out here, you can always make 2 of these events happen simultaneously in one reference frame. You can always find a reference frame in which these 2 events happen at pretty much the same time. Here, these 2 events happen at pretty much the same time. And if you look over here, now these 2 events happen at more or less the same time. This helps illustrate how, if we had fast-light communication, we could exploit various reference frames to send information back in time. Another thing you might want to take a look at is this diagram right here that displays a similar phenomena. It shows relativistic phenomena in a more understandable context. What here we have is a universe where the speed of light moves at 1 meter per second. We have a train that is moving at half the speed of light, and we have a man on a magic carpet that's moving at 80% of the speed of light. And we also have two lightning bolts that fall from the sky and produce a pulse of light when they touch the ground. The first pulse of light creates event A. The second pulse of light creates event B. By adjusting the value of U, we can see how this simulation looks in another person's reference frame. So if we set the U to 0.5, that shows us what things look like from this guy's reference frame, from the reference frame of the train. In this reference frame, he sees both of the lightning bolts fall diagonally and then create a pulse of light when they touch the tracks. He sees these two events happening simultaneously. If we look at what these events look like from the reference frame of the guy on the magic carpet, which is 80% of the speed of light, he sees two lightning bolts fall as well, but he sees the second lightning bolt fall first, and the first lightning bolt fall second, such that event B happens first, and then event A happens. This is the relativity of simultaneity, probably the hardest concept to understand for newbies to special relativity. I forgot to mention that if you want to see more events, all you have to do is input more values down here. This will allow you to use more events than the original 3, or actually the original 2. And you can actually specify their exact numerical values in our original reference frame. This is for the x-axis, this is for the time axis. Also, I should mention here that each one of these stick men over here has their own clock. It's supposed to measure time in their reference frame. The idea is these cycle around once every second in their own reference frame. If you want to know exactly how many cycles they have done, you need to click clock cycles over here. If you click this little circle over here, it'll tell you each clock will have this value inside of it that tells you how much time has passed, or how many seconds they have counted. In this case, it's negative because we're at a negative time value. If you go to a positive time value, you see here, it's measured about 1.5 seconds. If you want your own custom clock, because you don't think I've put clocks in enough places here, you can use this. You can use this option right here. You can place your clock wherever you feel it's appropriate, and you can change the reference frame of the clock you're using. So here, this shows us what the clock would look like if it were moving at half the speed of light. And you can set it all the way up here over to 90% of the speed of light. And that should probably help you get a better grasp of what's going on if you still have any questions about how this stuff works.